Bismillahirrahmanirrahim. Respectable Mr. Masroor Ahmed, Chairman, Oil and Gas Regulatory Authority, respectable Mr. Ehtisham Khattar, Senior Project Officer for Energy, Asian Development Bank, respectable Mr. Yusuf Siddiqui, CEO Anglo Energy Limited, Mr. Stephen B. Harrison, International Expert for Hydrogen, Mr. Nadeem Javed Bajwa, MD Inter-Service Gas System, Dr. Sardar Mozam, the Managing Director of National Energy Efficiency and Conservation Authority. Ladies and gentlemen, Assalamu alaikum. I'm so sorry. Respectable Mr. Musaddiq Malik, ex-Minister for State for Petroleum. Assalamu alaikum, sir. Special Assalamu alaikum, sir. We have reached the apex to welcome your dignitaries. We are surely excited to have been in this exciting and productive forum. I, Saima Shafir Rahman, shall be your host for the day. Dear audience, let's start this exceptional session by acknowledging the ultimate power of the Supreme Being, the one who possesses unlimited power and knowledge. Sadaqallahul Azim. The National Energy Efficiency and Conservation Authority is dedicated to providing sustainable and affordable energy efficiency and conservation options for the people of Pakistan. The authority strives to promote energy efficiency values across 5 major sectors, including power, energy and gas, transport, building, industry, and agriculture. I humbly request Dr. Sardar Mozam, the Managing Director of NEECA, to take the stage and deliver the welcome remarks.
Bismillahirrahmanirrahim. First of all, thank you all the participants, and I'm really delighted and happy and excited that we have such a well-distinguished panel with us. All the team members and the panelists we have today, I think it's a very privilege, sir, for us, especially Musaddiq Saab, for joining us today. And I think over the years, I think one of the aspects when we started reviving NEECA, that we have never seen people like you coming to NEECA and giving us this important and especially along with the other technicians with us today. I think it's something that we really wanted, that energy efficiency and conservation should be on the top agenda. And in the future, we should look into that aspect and design our policies, programs, and overall the landscape of the country where energy efficiency should be one of the key pillars. And I think we now see some of these things happening around and some of the interest from all the sectors, from all the top hierarchy, the individuals, and we're very excited that we are not only addressing the energy sector issues and taking maybe a small baby steps in that direction, but along with that, we are also addressing the climate change mitigation aspects. And I'm really happy to see Ministry of Climate Change with us today, along with the GIZ representatives and other government officials and donor agencies with us. Thanks to Asian Development Bank, because I think initially when we were discussing about this hydrogen study, ADB supported us to start this study, conduct this pre-feasibility study with the experts. And I would thank Toru, who was the energy specialist, who planned, working with ADB, initiated, worked with us, Stephen B. Harrison, Dr. Nadeem Javed, and other team members who, during all this process, were very supportive. And it took us quite some time to prepare the study and look into different options. I must say that a lot has changed when this study finalized till that day. And that's one of the reasons that we requested Stephen B. Harrison, who is the consultant with us, that he should also share with us some of the latest trends internationally and how these will be reflected overall in our future discourse on the hydrogen. So I think with this, I would thank you, all of you once again for being with us today, and all the participants who are joining us online. Really grateful for joining us today and taking such a huge interest in this whole process and this whole exercise. And I think we definitely look forward that this will be the future, that what we are trying to sort of understand and take it forward. And some of the demonstration projects, we will definitely, the next step moving out of it, that there should be not just talk, but implementation, and then how we can effectively develop our economy around the hydrogen fuel in this country. Yes. So thank you once more. And with this, I would request the next session with Nadeem Javed and other presentations will be presented. Thank you.
Thank you so much, sir. Ladies and gentlemen, reliance on imported fuel and high energy prices at the global level made it difficult for Pakistan to manage a reliable and cost-effective energy supply. Given the circumstances, the development of indigenous alternate renewable energy resources is a viable solution to address energy supply challenges. With this, I would like to invite Dr. Nadeem Javed Bajwa, MD Inter-Service Gas System, to present a presentation.
Dr. Nadeem Javed.
With this, I would like to invite Dr. Nadeem Javed Bajwa to present a Dr. Nadeem Javed to present a presentation on pre-feasibility study for Pakistan's green hydrogen study. I would mention that we would present this presentation online.
Thank you. I'm audible. Is it okay? Yeah. So, first of all, let me thank the organizers for this opportunity. And before I start, the Senator Dr. Musaddiq Malik, Mansoor Khan, Chairman Ogra, and all other respected dignitaries and the participants, very good afternoon. So, and a little correction, please. I'm not MD, NTD. Nadeem Javed.
नहीं सर उनकी आवाज आ रही है माइक पर
जी, should I start?
बोले सर एक मिनट yes sir now you can speak.
Okay. So let me share my presentation here. A little correction, as I was saying, that I'm not MD NTDC. I'm the former chief economist, and right now I'm a professor of economics and strategy at Karachi School of Business and Leadership. So this study, which I'm going to present now, is a bit, slightly old work which we carried out along with Asian Development Bank, and the NEECA was the collaborator on this in Pakistan during the COVID days. So, but yet, some of the findings are quite revealing, and the kind of this work could be used as a fundamental work for taking this important dimension into consideration in the future. So I have structured my presentation in a way that first I'm going to give you this context. That's hydrogen is accelerating, and it's important to know about it because yesterday I was just looking at the post which NEECA shared on the social media platforms, and there were a lot of negative and cynical comments regarding keeping in view the Pakistan's economic situation, and then taking this journey on hydrogen could be kind of a very misleading kind of thing. Then some of the experts or the people in the field are of this view. So that I want to correct with the help of a few slides. Then hydrogen for Pakistan. We mapped 13 value chains in the first place. And subsequently, while having with the meeting with MD NEECA, Dr. Sardar Moazzam and his team, we then finalized out of these 13 value chains, only 3 value chains for which we conducted very rigorous analysis, which I'm going to present in the subsequent slides. And then out of these 13, this is the case number 3 is on Ghazi Brotha Dam. The case number 6 is in Qaid-e-Azam Solar Park with gas grid injection. And the case 13 is run of the river micro hydro in the north. It was a kind of a hypothetical project for which we conducted all the surveys and did some cost analysis, and then modeled it into the financial kind of way to analyze that what are the possibilities of its feasibility in the days to come. And then at the end, I will present some concluding remarks, particularly some insights from this analysis which we carried out. So, going forward, as most of you know, that hydrogen will have a significant role to play as a clean energy vector in the future energy mix. Some examples of applications that become competitive are the first one, commercial vehicles, trains, and long-range transport applications are going to compete with low carbon alternatives by 2030 due to lower equipment and refueling cost. And if you look at that, this ministerial group of the Paris Agreement, or where they have agreed to have 10 million vehicles which are going to run on the hydrogen by 2030. And this is a very ambitious target, but seems like the data which is now available, that they are quite in line with this progress regarding this target. So then hydrogen boilers will be a competitive low carbon building heating alternatives, especially for existing buildings currently served by natural gas networks. Then the third application is industrial heating. So hydrogen will be the only viable option to decarbonize in some cases, besides balancing the power system as hydrogen production cost drops and demand is going to increase in the days to come. Then low carbon and renewable hydrogen will become competitive with gray hydrogen used for industry feedstock today as costs are falling and carbon price is rising with the passage of time. So these trends are very much highlighted in this slide, or where you could see that the drivers are highlighted on the left hand side, which shows that there is a stronger push to limit the carbon emissions. 10 years remaining in the global carbon budget to achieve the 1.5-degree goal. And right now, 66 countries that have announced net zero emissions as a target by 2050 are focusing on this. And out of this, 18 countries have a clear roadmap which they have announced to, follow the hydrogen, green hydrogen as major vector in their energy mix. Then there are, a very visible trend which are showing that the costs are falling of the renewables and hydrogen technologies. So roughly there is an 80% decrease in global average renewable energy prices since 2010. And this is a big, you could say, that push. And roughly 55 times growth in electrolyzers capacity by 2050 versus 2015 is also making hydrogen a kind of a very viable technology in the days to come. There are few indicators which are also, showing that there is a growing momentum when it comes to the strategic push in national roadmaps. Roughly 70% share of the global GDP is linked to the hydrogen country roadmaps data, which are these 18 countries which I've just mentioned. So these 18 countries almost compose of or contribute to 70% of the global GDP. And they are very hawkish on hydrogen as an important vector of energy in their energy mix. So roughly 10 million is the target for deployment of FCEVs announced at the Energy Ministerial Group at Japan. So 60 member countries of the Hydrogen Council today are there from the 13 member countries in 2017. So roughly 30 plus major investments are announced globally since 2017, and new segments like heavy duty, particularly the rail transportation, is also going to be envisaged that's going to be run on the hydrogen. So having this kind of the trend and key indicators in mind, so there is a possibility that scaling up of the full value is the key to unlocking the potential applications. And there is a 60% cost reduction of hydrogen by 2030 for the end users. And by having this, this is very important finding of the research, which has been recently carried out and which highlights that the subsequent study, I'm going to show some of our results which are not very encouraging, but keeping in view this trend, those results become very encouraging. So then hydrogen could meet a significant share of global energy needs competitively. So roughly that the share of global energy demand where hydrogen applications can compete with other low carbon alternatives by 2030 is roughly 15% plus. So that's a kind of a huge share then in the energy mix if we look at the current scenario. So then why hydrogen for Pakistan? So keeping in view that we analyzed that 11th 5-year plan, Vision 2025, and then the most of our annual reports on energy, state of energy in Pakistan are highlighting that these are the strategic energy priorities of the government of Pakistan. Number one, national energy independence, then continuous energy supply security, affordable energy. These first three include, then, combining it with the kind of 2022 floods over where this climate change has further necessitated that we should also opt along with the rest of the world this carbon neutrality in the days to come and reduce the pollution levels in our country. And besides that, also to enhance our export revenue by having this important vector in our energy mix. If it is going to be used in the country, then it is going to save the precious dollars. We can export it, but since there is a lot of potential to produce it in Pakistan. And then the last one, leveraging existing energy infrastructure, which is very much there, which I'm going to show you in the next slide, that shows that blending hydrogen into the high pressure gas grid transmission must be evaluated very carefully, as there is a possibility to add mix roughly from 2% to 8% in a very safe range. But then it could even add up to 12% as per the, international research shows. And Dr. Stephen is along with us, who is an expert on this area and a kind of a mentor for me as well when it comes to the technical side of this important vector of energy. He will also highlight this. So then there is a possibility of some low pressure natural gas distribution sections, which could be augmented by adding hydrogen by blending into the existing infrastructure of the gas pipelines in Pakistan. So once hydrogen is mixed with natural gas, there is, there is no additional cost. And if there is a cost, then that is very minimal cost. But when it comes to separating it from the natural gas, then it takes a lot of, you could say, effort and cost. And then converting some existing pipelines for pure hydrogen transmission may potentially be more attractive than blending in the broader grid. Then hydrogen for low temperature domestic heat is broadly regarded as one of the least beneficial uses of valuable green hydrogen. As compared to, burning it in for the fuel as a cooking, it is a more important vector to be used for power turbines and boilers, as well as for the transportation infrastructure, transportation networks. So, keeping in view these benefits and gains, there are a lot of potential gains to opt it as an important, important vector or driver in the energy mix. So going forward, we mapped 13 value chains, but just due to the paucity of time, I'm not gonna develop on that, because since this presentation would be available to all participants after the event, and you can go through it. So, but these 13 value chains were very clearly mapped over where some business proposition was existing, and then these 13 propositions were presented to NEECA, and then the NEECA proposed, keeping in view multiple aspects, along with the team of experts which were working on this study. We then just finalized these three projects. The number one is project number 3 out of these 13, which is use of power to produce hydrogen for the gas admixing between 2 to 6% at Ghazi Brotha run of the river hydro dam. Then project number 6, which is a kind of a Qaid-e-Azam solar park, over where hydrogen will be produced. And there are different variants, which I'm going to show you in the next slides. And then this will be transmitted to some, nearby station, or where then it could be admixed to the existing pipeline network. And then number 13 was a proposition, or where a micro hydropower for grids is going to be established in the northern Naltar Valley of Gilgit-Baltistan. And then this micro run-of-the-river grid is going to produce electricity. Besides, I mean, for 9 months, it is going to produce the hydrogen as well as a byproduct, which is then going to be used to run that grid or the turbine for more than, I mean, 1,000 villages nearby the Naltar Valley to provide electricity during the cold winter over where then the run of the river water is not available in the valley. So these three propositions are then uh, further evaluated by having the financial modeling. This is the methodology and key assumptions which we used for our financial model. The first one, we use the discount rate of 7% per year uh, as it is the, I mean, same benchmark which is being used in the planning commission for evaluating any long-range projects in Pakistan. So then tax and duty on the imported capital machinery, 25% was used, because if we looked at the HS code related to the electrolyzers and all that equipment which was needed for these value chains to establish in Pakistan. So, I mean, similarly, we use the similar taxation structure or tariff structure in our modeling. So then hydrogen energy value substitutes an equivalent amount of energy from LNG or LPG or some timber wood, or I mean, because in northern areas it is not the normal wood, it is a kind of a good quality timber wood, near good quality timber wood, which is being used. So we use the pricing of that wood as a proxy to benchmark the benefits of having this much energy available in the northern part of Pakistan. So then regarding the gas pricing, these 6 scenarios were used depending upon the value chain we were modeling. The first one, local natural gas at wellhead cost. At that time in 2019, 20, these were the prices, $125.44 per ton, and there is $2.23 per MMBTU. So LNG at Qatar contract prices, we use 2.23 MMBTU. So then average of the contracted and winter spot price, there was $7.36 per MMBTU. So then high LNG winter spot price, that was $10.27 per MMBTU at that time. Then imported LPG price, that was around $8. And then average of LPG and local natural gas price at the wellhead, there was $5.12 per MMBTU. But we also kept in mind that all prices mentioned in the dollar per ton were adjusted for calorific value while converting them from MMBTU to the tons, which these numbers are reflected in this slide. So then subsequently, the fifth assumption we used was the power purchase price at the relevant industrial tariff for the generation mode. Hydel or solar has been used where power supply access is possible. And these were the tariffs which were prevailing at that country in the country. You could see that the hydro was the cheapest one after nuclear. But eventually on the nuclear, there was no possibility to place electrolyzer. So we kept that, keeping in view the other sensitivities, defense-related sensitivities in mind, out of our analysis. So that's why we focused on the hydro, because, and then besides hydro, we focused on the solar. The rest of the energy and the coal and wind power was excluded at that time. So then more land. So in the sixth assumption, in each case, capex investment in self-generation or for the electricity was used as an alternative power supply cost basis. However, no land purchase, land lease charges were assumed for the electrolyzer equipment or hydrogen gas pipeline. Reason being, we were of the view that these are going to be placed on the existing facilities of the government of Pakistan. So, I mean, that's not going to involve a lot of new land, acquiring new land or acquiring new right of way. So that's why we excluded that part in our costing analysis. So then CO2 emissions taxation rate at zero. That is the prevailing situation in the country. But then hypothetically, we used a $40 per ton and $80 per ton as two possibilities just to evaluate the feasibility if in near future these kind of taxation is being introduced in the country. So then electrolyzer capex cost at 50% because some Chinese electrolyzers as compared to the European or Western electrolyzer manufacturers are available. So we then also ran few models by reducing the cost to 50% so that if the Chinese electrolyzers are being used, then what is going to be the implications on our net present value and economic rate of return. So besides this, we carried out sensitivity mapping for each scenario by using the 10% increase in cost. Then subsequently, another scenario for 20% increase in cost. And then the third scenario where we increase the cost by 10% and decrease the benefits by 10% just to adjust for, I mean, if this kind of possibility is going to be there, so then how it is going to impact the financial viability of these projects. So our calculations also included additional factors that are region and application specific, such as the cost of storage, compression, transmission, and topography of the region or where these value chains are going to be established. So uh, that shows that hydrogen is not self-consumed in few cases, though we not accounted for the taxes on the entity operating the plant, which could be province-specific taxes or also depends on the business model. Like, for example, hydrogen could be produced for the self-use and it could be used for the sale in the market. So this is the kind of a caveat to our analysis. But these simplification doesn't mean that the cost estimates are more generalized because we think that these are not too loose and these can be very easily adapted for the necessary considerations if some more specific and advanced level analysis are required in this context. So, I mean, after giving you this, overview that how robust and rigorous this analysis was, which we carried out, now I'm moving to the key findings of the analysis. So, I mean, these are the life cycle, you could say that pie charts, which shows that the major cost is electrolyzer when it comes to the 100 megawatt electrolyzer being installed on the existing Ghazi Barotha turbines. Then, but the annual power cost is 29%, which is a huge cost. So then in the subsequent model, we analyzed the another possibility over where we produce this electricity ourselves by adding an additional turbine on the existing Ghazi Barotha dam, and then analyzed that what is going to be its implications. Then, moreover, then we also analyzed 1 gigawatt turbine and as well as 1 gigawatt electrolyzer to be installed, and then looked at the possibilities. So these you could see over here. Then all the four scenarios regarding the uh, proxies, which we use the local natural gas, then LNG at the Qatar price, all those 5-6 scenarios which I presented in the previous slide were analyzed. Subsequently, the similar situation was analyzed on 1 gigawatt power plant and electrolyzer. But unfortunately, you could see that there is a serious reduction in the levelized cost of hydrogen that goes from $4.16 to $2.92. Okay, but when it comes to and then the levelized cost of energy, which is being used here, is 4 cent, because we are having our own capex to produce electricity to run this electrolyzer on the Ghazi Brotha Dam. But unfortunately, there is no scenario which is feasible. Uh, Even if we, include the carbon emission tax at $40 and even at the $80, even then it does not make sense to produce hydrogen and subsequently use it. But there is one scenario over where, sometimes in the winter season, as you know, the water run of the river water decreases, and eventually the whole transmission mechanism is designed on that optimal level to evacuate power from the Ghazi Brotha Dam to the national grid. So when in the summer seasons, the run of the river flow is at its maximum, so then at that time, the energy being produced is on a higher side as compared to which is being evacuated. So there is an energy loss, electricity loss during those 3 months, which we confirmed from the experts at that time. So then we ran one possibility that if this energy is free of charge available to run an electrolyzer of 100 megawatt, so then the levelized cost of hydrogen goes down to 2.74. And eventually this becomes feasible, slightly feasible. And then this hydrogen could be used to run a fleet of at least 30 buses at the Islamabad airport or any other, near Nowshera or Peshawar BRTs or whatsoever. So that was one of the possibility that we. Similarly, then we ran the sensitivity analysis on the similar lines, which I mentioned in the previous slides, over where I was mentioning the methodology. So unfortunately, again, there is no, possibility of feasibility under any scenario which we ran on this model. So let's move to the next case. That is Quaid-e-Azam Solar Park with gas grid injection. Here we had 3 major possibilities. The one was 100 megawatt option at the existing solar park, over where then we have to purchase the electricity from the solar park, and its annual power cost is going to be then 25% if you look at the life cycle cost of the total project. And then the life cycle of the project is 30 years in all the value chains, as per the criteria being used in the Planning Commission of Pakistan. So then we ran another possibility over where then power will be uplift by adding CQ solar system of an additional 100 megawatt and then placing 100 megawatt electrolyzer on it. And then third possibility was worked out over where then 1 gigawatt uplift of the solar park, besides placing 1 gigawatt electrolyzer on the solar park. Then in that scenario, you could see over here in the second scenario, the capex increases, but eventually the annual energy cost goes down. But eventually in the, over where then we want to achieve the economies of scale by having 1 gigawatt uplift. So then the capex even further increases, and then there is a massive decrease in the unit cost of electricity. That's the levelized cost of energy goes down, but yet the level of cost of hydrogen is not good enough. That's going to make the project feasible. So these are the key findings or the results. You could see over here, this is the option 1. Over where the levelized cost of hydrogen is $8 per kilogram. It goes to $3.3 per kilogram when we have capex to have our own electricity by uplifting the energy system over there. and then it goes to $3.7 per kilogram when we, increases the size from 100 megawatt to 1 gigawatt. But eventually, the levelized cost of energy goes down from 0.05 to $0.03 per kilowatt hour. There seems that there is economies of scale when you expand the size of the solar park, but there is no economies when we move from 100 megawatt to, sorry, yes, 100 megawatt electrolyzer to 1 gigawatt electrolyzer. There is a certain reason which I will explain in the conclusion slides. So subsequently, at $40 and $80 tax emissions on the carbon is not going to make this value chain feasible from any angle. Subsequently, then we carried out the sensitivity analysis along the similar lines, but unfortunately, again, there was no impact on the feasibility of any of these value chains which we analyzed in this mega project. So now let's move to the 13 case. There is run-of-the-river micro hydro in the north. Over here, as I mentioned, the objective was to have a possibility to produce electricity on the run of the river. Then besides producing hydrogen as a byproduct or as a side product, then to be used for the 3 months in winter when the water is not available, and eventually then there won't be any availability of the electricity. And it could be a microgrid solution for 1,000 small villages of 200 to 300 housing units for every village. So eventually over here you could see that we ran 3 scenarios over where the local natural gas and imported LPG prices were compared. Since no pipeline gas could be provided over there, so we haven't used that as a proxy to benchmark the benefits. But eventually, average of LPG and local gas prices, we used another scenario. But in all these 3 scenarios, there is no possibility that it could be feasible. So then we thought that it is a very, deforestation is a major problem in that area, which could be curtailed if we provide the same hydrogen for as a cooking fuel in the small cylinders or through the small pipeline network in that area. And then these housing units could use hydrogen as a cooking fuel by, saving that good quality timber which is being used over there. And then it can stop the deforestation as well. And then eventually the wider economic benefits could not be captured, but the same wood which is being used at the local prices in the Peshawar, and then slightly a higher price level for the good quality wood which is being burnt in these northern areas were used as a proxies. But unfortunately, again, the levelized cost of hydrogen is very high. That is $30 per kilogram, though the levelized cost of energy is 10 cents by having this microgrid over there on the run of the river. But yet, this scenario is not a very feasible scenario. But eventually, if the wider economic benefits like stopping the deforestation in that area is being incorporated, then this becomes slightly, closer to feasible. Then its cost-benefit ratio becomes 1 to 0.98. Very closer in the very close range. So then we ran the sensitivity analysis on this value chain as well, but unfortunately, no scenario could become feasible along the sensitivity. You could say that analysis as well. So if I compare all these 3 key value chains and then their subsequent different options within every value chain. So this is the kind of situation. The levelized cost of hydrogen increases when we move from Ghazi Brotha Dam to the run of the river micro hydro in the north of Pakistan. Eventually, then the levelized cost of electricity uh, goes, down, uh, but it increases again in the northern part. Levelized, then economic rate of return, you could see that that is mentioned or highlighted with the help of this orange curve, is also, quite dependent on these two major factors, particularly which I have mentioned over here, that using uh, uh, this producing the power, uh, 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 you could say that it could be hydropower or it could be the solar power, is always more attractive, because then the levelized cost of energy is very cheap in that option. But then using the investment in self-generation, levelized cost of energy and levelized cost of hydrogen are in the range of international benchmarks for similar schemes, though they are not feasible in Pakistani context. Why? There are certain reasons which I'm going to mention in the next slide. So then better electrolyzer utilization also favors the Ghazi Barotha Dam, because it is on the run of the river. For 3 months, it is going to consecutively run on the river. But in case of solar power plants, because the solar power could be generated roughly from 9 to 11 hours during the daytime, then because of that, electrolyzer efficiency goes down to 41%, as compared to 95, 96% in run of the river projects. So this reduction in the efficiency on the solar power, though the solar levelized cost of energy is much cheaper, this value chain doesn't become economically, you could say that, feasible. So
ये 949 कैंडिडेट्स सिंध असेंबली की जनरल सीटों के इलेक्शन लड़ रहे हैं पार्टी टिकट्स के साथ। इनका जरा सा डेटा अगर मुझे मिल जाए कि कौन सी
could
पार्टी
you
से
please
कितनी
could you please let me finish? Could you please let me finish, and then we will have the question, please.
मुझे ये डेटा मिल जाए कि हर पार्टी से कितने उम्मीदवार हैं, कब ब्रेकअप मिल जाए पार्टी वाइज।
Azim Saab, please let me finish, and then of course you will have the floor and you can, raise your concern. Please let me finish. So the micro hydro with standalone power system has a high level of intangible benefits, uh, but it fails to make an attractive business case.
क्वालिटी वो खराब थी काफी, वो
The bankable, can you hear me please? Because the host has muted everyone.
Yes, sir, we can hear.
Yes. So bankable investments related to hydrogen deployment in Pakistan will require policy support, as under the current regulatory power tariff and taxation framework in Pakistan, no major bankable projects have been found to be possible from the cases analyzed in this study. So removal of import taxes on the purchase of high technology capital equipment such as electrolyzers or related equipments from international suppliers is important step in that regard. So CAPEX reduction of major capital equipment, which are possible today using Chinese suppliers, and further reductions will come as this technology matures. And this is what I have shown you in the major trends in this industry, which are shaping this industry right now. So then the current power pricing tariffs do not support use of curtailed supply for the hydrogen generation, as I have asked for 3 months supply, which is available due to, not evacuation to the national grid. So, but some, you could say that for a framework is required so that hydrogen could be produced from this excess power from the power generation during the times of peak demand. So a tariff policy review to enable this would support the business case for investment to enable the power supply security. So then the fourth key insight is that hydrogen has huge potential to curtail carbon emissions. But in the absence of any reasonable national benchmark for carbon emissions cost, it is difficult to quantify, monetize the benefits. So a carbon, you could say that emission tax or wider greenhouse gas tax will support the decarbonization investments in the country. So to use the hydrogen, particularly to displace the diesel for mobility auto applications in the country, can support air quality improvement and public health. Besides, dealing with this ongoing, you could say that crisis of fog and smog in the major cities of Pakistan, that is going to have heavily, you could say that is going to burden the polluted urban areas, could be reduced. But with carbon emission quantification of the benefits and development of the business case is required in that case. Besides, development of a regulatory framework for underground hydrogen storage in new salt caverns would make the case of the highest LNG cost analyzed very realistic. And then the last one, alternative hydrogen production technologies and utilization cases may also be could be a bankable projects. Only 3 out of 13 proposed value chains were analyzed in detail through this study because that was the scope of the work which we took as consultants. So this study has therefore not been exhaustive in conducting a detailed analysis of the breadth of the options for hydrogen deployment in Pakistan. So therefore, no future strategy on the basis of these value chains which we mapped, by treating them that these are not feasible is not going to be a wise approach. Rather, there could be a lot more potential, keeping in view then this time lag also over where some of the key developments had happened, on which I think Mr. Stephen will, who is the guru of hydrogen, and I also learned a lot from him being the team lead in this assignment along with NEECA, will also highlight in the subsequent presentation. So with these, key highlights and insights, I would like to thank you for your attentive listening. And over to NEECA, please.
Thank you so much, sir. It was really an amazing presentation. With this, ladies and gentlemen, I would like to invite Mr. Stephen B. Harrison, international expert on green hydrogen. Thank you so much, Mr. Stephen, for joining us. You will be presenting Pakistan's current energy situation and the future role of hydrogen energy.
Thank you very much. Can you hear me, please? And can you also confirm that you can see my screen?
Yes, Stephen, we can hear you, please.
And can somebody confirm that you can also see the screen that I'm sharing? Has that
Yes,
worked?
we can see the screen.
Thank you very much indeed. I'm just trying to adjust things so that I can actually see myself as I present here. Otherwise, it's a bit difficult for me. So firstly, thank you very much indeed to Dr. Nadeem for his presentation today and also his friendship over the last 4 years. And thank you also to the esteemed colleagues at NEECA for the invitation to speak today. A lot of things have changed. A lot of things have changed in the world of hydrogen since we did the study. And I would also underline, as Dr. Nadeem said, the 3 cases that we looked into in detail were simply 3 of 13. And if I were to have my time again, with the experience that I now have and the world has 3 years later, I think perhaps we might have picked different studies that could have ended up being significantly more economically attractive. Things have changed significantly, and it really is worth having another look, I think, is my main and key message to you, which I think is the message Dr. Nadeem was trying to explain in his last slide. So let's see what's been changing in the world today. Here are what I regard as 10 key shifts that have taken place, some of which we accounted for in our modeling. For example, the expected cost reduction of Chinese electrolyzers, we modeled for that. But other things have also changed. Just to be very, very clear about one of the examples that's changed is the whole shift towards hydrogen derivatives, such as ammonia and methanol, has really taken off. So people are asking the question, hydrogen for hydrogen or hydrogen for ammonia and methanol. And once we start looking at hydrogen for methanol, then of course we can convert methanol to DME, dimethyl ether, and dimethyl ether is a substitute for LPG. So when Dr. Nadeem was speaking a moment ago about providing heat for cooking and heating in very, very remote regions, we were looking at doing that through hydrogen and making hydrogen locally. If I were to have my time again, I think what I'd be saying is let's make renewable LPG, effectively let's make DME, dimethyl ether, and transport that into those regions and provide them with enough inventory to cover the winter. So I think what the world now knows and what I now know would really, I think, cast different light on the work that we did and or would do if we were to come back into this area. Let's cast our minds back 100 years to the first big hydrogen project that ever took place, and this was in Norway at more than 100 megawatts. So this is comparable to some of those big hydro projects that Dr. Nadeem was explaining to you. The reason for making hydrogen was not to make hydrogen. The reason for making hydrogen was to make ammonium nitrate fertilizer. And again, we're coming full circle with the appreciation that hydrogen derivatives can be more valuable products than hydrogen and are certainly easier to transport and store. On the Aswan Dam in Egypt, the two projects on the left here, and also another project in Norway, all of these projects went to ammonium nitrate as a fertilizer. On the left here, Kwekwe in Zimbabwe, that was also ammonium nitrate for use in the mining sector and also as a fertilizer. Here, 2 cases in Quebec in Canada, all of these running off hydropower. All of those projects, which were about as big as anything we're doing today, have now closed down. Why? Because making ammonia or ammonium nitrate or urea fertilizers from LNG, from liquefied natural gas or pipeline natural gas, was cheaper. On the other hand, we're now seeing, in some cases, rising LNG, imported LNG prices and a drive to decarbonize and defossilize. So there's a huge motivation to look again at those big hydrogen projects, just like we were running 50 years ago. And as you can see, the electrolyzer on the left there was exactly the type that was installed in Kwekwe. And even the electrolyzer technology has been rejuvenated by a German company called Sunfire. So we're seeing the whole clock turn back between 50 and 100 years, and we're reinventing what we have learned and done in the past. This is the biggest green hydrogen project that's come through FID, that's come through financial close and is actually in the execution phase. This is in Saudi Arabia, in NEOM. This is a 2 gigawatt project, and you might remember that we looked at projects up to 1 gigawatt through our study. And so this is again of a comparable size. Interesting to note here that the hydrogen is not being made for hydrogen. The hydrogen here is being made for ammonia as a tradable energy vector. Again, don't always assume that the hydrogen will stay as hydrogen. Think more broadly to other hydrogen derivatives. That's exactly what is being done in this project in China. Ammonia, again, is the target molecule, but of course we need to start with green electrons, then make green hydrogen, then make the green ammonia. And it's interesting that this particular project uses a combination of electrolysis technologies from alkaline that we evaluated heavily a few years ago, and includes an element of PEM, which is a different electrolyzer technology that typically costs a little bit more to deploy, but has the benefit of being able to work with intermittent power. So it switches on and off more easily. So the beginnings of PEM electrolysis you can see here were through the General Electric Company in the United States and Siemens in Germany around about 50 years ago. And this is a modern PEM facility on the left, 10 megawatts in Germany, on the right, 20 megawatts in Canada from ITM Power and Cummins. And here's a large Siemens PEM electrolyzer on the left, just been delivered and waiting to be installed at an e-methanol facility in Denmark being operated by European Energy. Again, I keep coming back to this point that a lot of hydrogen is being converted to other chemicals, typically called hydrogen derivatives, such as methanol and ammonia, because they are higher value and easier to transport than hydrogen. Taking a step back, if we want to make hydrogen or even those hydrogen derivatives, we must recognize that the vast majority, if we look at raw capex of a fresh greenfield site project, the vast majority of the capex is going to go into making those green electrons. And you saw that very clearly from one of the pie charts that Dr. Najim put up when we considered self-investment in a new turbine at the Gazibo Rotterdam. Suddenly that was 3/4 of the project capex and the electrolyzers were looking cheap. Whether it's wind, solar, or hydro, the same holds true. What it really means is that we need to focus on green hydrogen projects in parts of the world or in parts of Pakistan where green electrons are cheap, where we've got good solar, where we've got good wind, or on the other hand, where we have curtailed power. And Dr. Nadeem made a few examples of the use of curtailed power when there's more power being produced than we can actually put onto the grid or recover. Free power. All renewables are variable. Everybody knows about the variability of solar. And what people don't quite know so much about is the variability of hydro. It's variable on a seasonal basis. And of course, wind just does whatever it wants to whenever it wants on a daily, weekly, and annual basis. But we can integrate and combine those various different variable renewable sources to give a relatively firm power profile, which can improve electrolyzer utilization and economics. And Dr. Najim was trying to explain this through some of his work. And the electrolyzer utilization can improve the electrolyzer economics. And a lot of historical projects have tried to increase electrolyzer utilization. And certainly if we're going through to derivatives such as ammonia and methanol, that can be helpful because the total project capex is higher. On the other hand, a large number of projects now are trying to look at the economics of using curtailed power or free power. And here's an example from South Australia, where solar dominates the grid in South Australia. And a lot of it is rooftop solar, which can't be turned off. And therefore, there are negative power prices for several hours a day, 6 or 8 hours a day. Now, what that means is that instead of you paying money to run your electrolyzer and purchase green electrons and make hydrogen, somebody else is paying you money to take those electrons off the grid. Somebody is paying you money to make hydrogen. It completely transforms the economics. And again, when we start thinking about these business models, we need to understand what is the power pricing strategy and tariff in a particular country. But whether or not the pricing tariff works in this way, the grid will be working in this way. Here's another case study from the United States using cheap power during periods of the day when the power is very, very cheap. And you can see that the lowest cost of production is operating an electrolyzer at 30% of the time. So you spend a lot of money to buy a very expensive piece of equipment, and you choose to only run it 8 hours a day instead of 24 hours a day. And that actually gives you better economics than running this very expensive piece of equipment 24 hours a day, because you're aligning its operation to periods of the day when the power price is cheap. This whole business of using curtailed power is a massive shift in the way people are thinking about green hydrogen projects. What that means, though, is that we must be using an electrolyzer technology that is able to cope with intermittent operation, on-off operation, that favors PEM or a new technology called AEM, which tends to be more expensive than alkaline. However, if we think smart, we can combine the cheaper alkaline electrolysis with the more expensive but the more flexible PEM or AEM electrolysis to generate an electrolyzer park that is well suited to variable or even intermittent renewable power operation. And when we modeled, we used McPhee as a Western electrolyzer provider, and a lot of the Chinese producers are also catching up with Western technology, and everybody's showing us a vision of large electrolyzer parks and how they will look in the future based on modular configurations. Pressurized alkaline is becoming a very, very standard technology, especially with some of the younger, newer Chinese electrolyzer producers who are offering the lowest cost alkaline equipment. And we can see here that the price for LONGi equipment is perhaps as low as $350 per kilowatt. But bear in mind, that's the purchase price of the equipment. Once it's been installed on site, you can perhaps say it's going to be 500, 600, maybe even $700 per kilowatt once you include the engineering costs, tie-ins, and site costs. But I would do say just a little bit of a warning here, please, to everybody, and the world has learned a lot over the last 3 years. Some of the technology and materials that the Chinese electrolyzer producers are using are different to what a Western electrolyzer producer would be using. And in fact, some of the Chinese electrolyzer producers shift the materials and the specification when they market their electrolyzers inside of China and outside of China. There are differences, real differences between the cheaper and more expensive technologies, and sometimes it's worth paying a little bit more to get something a little bit better. It really depends on the use case. And we learned that quite painfully, or Sinopec learned that quite painfully at this 260 megawatt electrolyzer park, which is the world's biggest electrolyzer park, which started up late last year. The promise from the Chinese electrolyzer suppliers was that it would be able to turn down to 50% of capacity, sorry, to 30% of capacity. The reality was that it can only turn down to 50% of capacity, and use of a particularly low-cost diaphragm material inside of the electrolyzer is the main reason for that difference. So we're learning as we go the strengths and weaknesses of various different systems, what to do, when to do it, what not to do, when not to do it. And the number of electrolyzer producers, whether they're Chinese or Western, is growing very, very fast. And the number of deployable, bankable technologies that we can consider is also growing quite fast. So alkaline and PEM are being joined by solid oxide and AEM. So the choice and diversity of technology and its cost point is shifting very, very quickly. And again, if we were to remodel some of these cases in Pakistan, we may choose different technologies and begin to get some different numbers coming through. I'm switching now a little bit, coming through more to hydrogen utilization, away from production through to utilization. This is a project proposed for the Netherlands. The reason I'm showing you this one is it combines something which I think is incredibly important for the future, and that's large-scale hydrogen storage in underground salt caverns. Now, not every part of the world is able to do this because you need to have the right type of rock and geology underneath the ground. You need to have large salt deposits, which do exist in the Netherlands. And if you can do it, maybe you should do it. I believe that the indications are there's a similar rock strata between Islamabad and Lahore in Pakistan that could also potentially be used. But bearing in mind that we're going to get more and more variability of the power production, more seasonality of rainfall, all of these kinds of things, power and energy storage to do short-term and long-term seasonal balancing is becoming more and more and more important. In this particular application, the hydrogen is going to be released onto a power generation turbine. Exactly the same scenario in the United States. This is the ACES project in Utah, electrolytic hydrogen, underground hydrogen storage, and that hydrogen being released onto a Mitsubishi Power specially adapted turbine to produce power to shave off the peaks in the power demand, just like the gas turbines in Pakistan are used as peakers. This would be a hydrogen peaker instead of a gas peaker. As I said earlier on, the indications are, you never really know until you start doing exploratory drilling, but the indications are that in several areas of the Potvin Plateau, underground hydrogen storage would be possible from a technical perspective. And if it can be done, it is by far the lowest cost way of storing hydrogen in large quantities over a seasonal basis to smooth out that massive peak in hydroelectricity production, as an example, or to smooth out wind and solar production peaks, or to smooth out the demand profile through winter and summer. I think Dr. Nadeem actually used this slide. I won't go over it in too much detail. We did look a lot at hydrogen blending into the gas grids in Pakistan through our previous study. Of course, it is theoretically possible. A lot of precautions would need to be taken, and I think it would be really good to look at the option of whether or not it's done on the transmission lines or the distribution lines. So theoretically possible. Whether or not you'd want to do it, whether or not there's a safety case for doing it, whether or not there are better things to be done with the hydrogen, those are all good questions. But this slide just covers some of the facts. The other pathway to green hydrogen, and I'm really pleased that Dr. Nadeem mentioned that other technological pathways can also be considered beyond electrolysis. And the other pathway to green hydrogen is through biomass, which is a carbon neutral feedstock. And we go through a gasification pathway to end up with hydrogen. We can also end up with a lot of other very, very useful fuels. And again, the example of methanol and DME is covered here. DME, that dimethyl ether, is effectively an LPG, a bottled gas substitute. The issue with using biomass as a feedstock, again, is seasonality. Hydropower is seasonal, so is harvest. And here are some various different harvests that take place throughout the year in Pakistan. Through some months of the year, we have plenty of post-harvest agricultural waste to make hydrogen with. And for a couple of months of the year, notably around September, August, and October, we're going to be a little bit lean. Whether or not you choose to operate on a 9 months a year basis is clearly one option. Alternatively, we begin to blend municipal solid waste, so trash, garbage, with some of the biomass and make hydrogen that way, and thereby mitigate the issue of seasonality. Clearly, the CO2 intensity changes when we do that. So the last slide, which I've just thrown in at the last minute, when I heard Dr. Nadeem talking about fuel in remote regions, again, just a quick reminder, please. Bottled gas, LPG, can be made in a sustainable way, either through electrolytic hydrogen or biomass to hydrogen, biomass to syngas, through methanol, and then to DME, dimethyl ether. And DME is effectively the best possible renewable substitute to LPG, which for Pakistan represents an imported fossil fuel energy vector, a bit like LNG. And if people are using, renewable dimethyl ether to do their cooking, they're either displacing imported LPG or displacing imported LNG potentially. So good in either direction, and also good for the climate. So yes, just summarize what how Dr. Nadeem closed also. We did certain things. Did we do everything exactly right? Did we look at all the right cases? Maybe, maybe not. We did our best 3 years ago. How would we do things right now with the benefit of additional 3 years of knowledge and how the world has changed? I think it definitely warrants taking another look at the deployment of green hydrogen from various different routes and pathways in Pakistan to support decarbonisation and to support the local economy. Thank you.
Can we ask the question?
NEECA are chairing the session. I don't really know what the agenda is. I'm very happy to take questions, but please can NEECA give some guidance on whether we do that now or later?
Well, thank you so much, Mr. Stephen B. Harrison, for a wonderful presentation and for your time. Well, ladies and gentlemen, let me have the honor to invite Dr. Musaddiq Malik Sahib, former Minister of State for Petroleum, for his valuable remarks on green hydrogen energy in Pakistan. Please, sir.
Thank you very much. First of all, thank you very much for inviting me. And I really enjoyed the presentation and learned a lot from them. I was a bit confused. I just didn't quite know what point of view to take. The technical point of view, the economic point of view, or the geopolitical point of view. And all of them are very important points of view. So I'll try to create a hybrid, talk less about technology because a lot of discussion has already taken place, transpired about the technology and so on and so forth. If I heard the presentations right, and a part of it I couldn't hear very clearly because I couldn't see, and what I can't see, I can't hear. At least that's what it tells me. It turns out that the feasibility study, it appears that in most scenarios, green hydrogen is not feasible in Pakistan, is what I heard. And I'm not surprised because I've been dealing with the energy sector. I've also dealt with the State Department in the United States. I've dealt with numerous countries in the GCC. And I've yet to come across one, and I'm not talking about 130 or 75 projects. One project which is economically viable of green hydrogen or green ammonia without subsidy. You can use fiscal instruments to create subsidy, like taxation, carbon taxation, or this money, or whatever you want. But I haven't come across, and I have not kept up with it for the past 4 or 5 months now, 4 months maybe. But before I left, I was deeply looking into it, and I did not or could not find a single project which was economically viable without some form of subsidy, some form of support. Let's not call it subsidy, let's call it support. You've also seen the limitations of technology, of electrolysis, particularly the limitations of scaling up electrolysis. It's very clear. And when the conversation started and references were made to Chinese technology, I was wondering about the scalability of the electrolysis technology the Chinese are undertaking. And right there, smack in the second presentation you saw what the scalability is. Under 30%, no, under 50%, it doesn't work. So all of these assumptions that we are making about technologies and so on and so forth, I haven't seen them forthcoming. Maybe they will come in due course, but they aren't there. So I find this right now to be an essential romantic idea. And I'm a romantic. So I'll flirt around with it and I'll go along and I'll wait for the technologies to improve and the efficiencies to come about. So as a romantic, I love this idea. As a country of 220 million people, where basically 80% of the people do not know how to put food on the table on an everyday basis. And they're struggling with the high cost of energy. To introduce another source of energy which is higher cost, as of right now, as a realist, makes very limited sense to me. Of course, Saudi Arabia is putting up 2 gigawatts worth of ammonia, green ammonia plants. But you know how much money is going into it and how much subsidy is going into it. And you know who all the collaborators are. So any country that has billions of dollars to offset its carbon footprint and has billions of dollars to invest in it should do it, can do it, are doing it. The question for me as a policymaker is, based upon these presentations, can we do it? And I would say, great romantic idea. Our carbon footprint, for your knowledge, is 0. If you made right now the heat map, you wouldn't be able to spot Pakistan. I'm not saying 0, I'm metaphorically saying, I'm saying Pakistan is not one of the highest carbon producing countries in the world. Pakistan does have a carbon footprint, and not for the sake of the world, but for our own sake, for the sake of our own children. We need to mitigate that risk because we are lying at the foothills of Himalayas like a valley. And with a slight change of pattern and the slight rate of melting changes, our entire barrage systems are going to get blown away. With a slight change in climate, our crops, our food security is going to become suspect. So for our own sake, we need to invest in environment. But today's conversation is not about environment, because we're completely, fully, 100%, and I never say 110% because I mathematically don't understand that. That's the limitation of math that I've learned, but 100% committed to climate. But can we basically, under these set of circumstances, move towards green hydrogen or green ammonia? Yes, we can, which is the discussion that I have with multilateral donors and bilateral countries with whom I interacted quite closely, the European countries and the United States. If they fund it, yes. If the funding is available, if the subsidy that is required is available, then the answer is yes. And if it's not available, we might not be able to do it. Right now, the cost of green hydrogen, with all of the technological things that we have spoken, the last project that was done in India was at $5.5 per kilogram to $6 per kilogram. Right now, the cost in the United States with all of the advanced technologies is $6 per kilogram. Well, we must know something a lot more than what the Indians know to assume $2.7 per kilogram. The end game is to bring it to $0 per kilogram through carbon offsets and so on and so forth. And that's where we want to go. But we're not finding the instruments to do that. I'm not finding, as a minister, I was not finding the marketplace where we could raise capital, green capital, to build this up and offset our carbon footprints. I went to several countries saying we're setting up a refinery with the GCC countries, with the participation and investment of GCC countries, and we want it to be carbon neutral. We'll set up the refinery, assist us in doing green hydrogen, to make sure that 100% of whatever carbon is produced from the refineries is more than offset. Didn't get any funding. I had lovely and fantastic conversations, but no funding. So I would urge a lot of our friends who are here, bilateral, multilaterals, help us. We want to do all of this. And it's not economically viable. And we're a poor country. And we also know that we're a debt-trapped country. We can't take debt. We can't take further debt because we'd be buried under the debt. And therefore, if some equity is available, some investments are available, some grants are available, we'd like to do that, and we'd like to pay back in carbon offsets. But some instrument, some framework has to come into play in order for us to do that. I mean, at $3 to $4 per kg, you're producing 12 to 13 cents electricity. I mean, you're taking 4 cents electricity, green electricity, green wind electricity or solar. And 4 or 5 cents, we're not getting it for more. We try it here. So the cost of capital, the cost of the investment in Pakistan is higher because of the countries. So we tried at 4 cents and we tried at 3 cents and we didn't get it. And let's say 4 cents or 5 cents, we get it. And then we convert that into 12 to 14 cents electricity. What sense does it make? And then we need another 12 cents to store it, or 5 cents or 2 cents. What sense does that make? So rather than producing 4 cents, 5 cents, 6 cents, 7 cents solar, we should end up producing 16 cents, 18 cents hydrogen. Unless the marketplace is there, unless the carbon offsets allow us and grant us investments, unless the green funds are there, we'll struggle. Because our reality is poverty. Our first and foremost commitment is to the people of Pakistan. And when I say people of Pakistan, I mean particularly and exclusively almost the poor people of Pakistan. And for any romantic idea, even if I have, and I love my own romantic ideas, I'm not going to put the people of Pakistan in the way of hardship. That ain't happening. So we'll have to find a new and interesting and collaborative way of moving forward. why do I take such a, so to say, non-fashionable view of saying what I've just said? Because we were made to believe very firmly that we are interwoven into a global fabric. And I was fighting to slow down on coal completely, personally, because I believed that environmental impacts of coal are detrimental. And then the geopolitics changed. And when the geopolitics changed, and the cost of LNG, as my dearest friend, Mr. Chairman would know, moved from $30 million to $35 million a cargo of LNG to $165 million per cargo that was sold by the UAE. And it was all driven by the European energy demand. When we looked at the world and we said, hey, we were all a part of the global fabric. The cost of LNG is moved from $35 to $160. What about us? And everyone told us, what about you? Go figure out on your own. So we've learned the hard way, my friends, that we'll have to figure it out on our own. So figure it out on our own. What we're going to do now. We're going to not make commitments to great ideas, but to the money and investment on the table. And if the investment is forthcoming, the green economy is booming, the green funds are available, the subsidies or grants are available, we'll go along. And if they're not available, we'll do what we must. Isn't it amazing that our coal was black and European coal, I don't know what that turned out to be, yellow with orange polka dots? What color was that coal? The coal mines in Europe were opened up. The coal power plants in Europe were opened up, and we were asked to shut them down because the world had to go green. So these two different colors of coal, of carbon, and different regimes. One, IMF saying no tax for you, and the other, everyone saying, particularly the Europe now saying, that if you don't do the carbon audits, we do not let your products come in. This is going to be the new industrial policy. This is the new industrial policy. In 2 to 3 years, if we don't have carbon audited products, first starting with energy intensive products which come from, these steel industries and so on and so forth, if we cannot produce the green audits, our products would not be allowed. And a new entry barrier is being created in Europe. It's called carbon tax, whatever. Carbon boundary, some tax, something. But this is the new industrial policy. Hey man, we have to deal with it. So we would. But right now we look at the world and we say, climate, interwoven into one global fabric. You and us together, our children together, interwoven in that fabric. Let's protect the climate together. So we'll make our commitments. And we look forward to carbon funding. Because in the absence of that carbon funding, this 16 cent, 20 cent, green hydrogen, green ammonia is a great romantic idea. So I was not cynical. I'd continue to romance with it till we can do something for real. Thank you very much for your attention.
Well, thank you so much, sir. With this, I am pleased to invite Mr. Yusuf Siddiqui, CEO, Anglo Energy Limited, for his thoughts on green hydrogen energy. Please.
Bismillahirrahmanirrahim. A very Assalamu alaikum and a very good afternoon, everybody. So good to see so many people coming today. The lights were good actually, but it's okay. So with all due respect to Mr. Sadiq Malik, I am not a romanticist.
but I'm cautiously optimistic. So let me give a very quick picture. Can you go to the second last slide, please, and just stay there? So just can you raise your hand? How many of you have some sort of a technical or a scientific background? Just raise your full hand. Good, 50%. That's healthy. So let me just paint the picture. Absolutely, I'm cautiously optimistic, but I think until we are not cautiously optimistic, we will not move forward towards a solution. So the hydrogen is the lightest element, very reactive, highly combustible. It has been used in the chemical study for industry for decades, primarily in fertilizer and petroleum refining. In 2021, the demand was 94 million metric tons. It is expected to go double by 2030. And particularly, the demand will come from the heavy industry, power generation, and the production of hydrogen-based fuel. This is pretty much a very clear-cut thing. In sources of hydrogen, more than 99% of hydrogen today is produced from fossil fuels, particularly natural gas and coal. With the global focus on energy transition, but for us, it's the energy affordability is more important than transition. It's extremely important. So my talk, very small talk for 5-10 minutes, will be through that lens of affordability. There's a lot of emphasis on hydrogen via cleaner or greener sources, as they say. The clean form of hydrogen today are blue, which is produced from fossil fuels, but with carbon capture, and green, which is produced from electrolysis with water as a source of renewable energy. This shift in production method can significantly impact the carbon footprint of the energy industry. Since hydrogen produced from coal and natural gas, and this is important, they emit around 20 kg and 9 kg of CO2 of H2 per kilogram of H2, while green hydrogen emits none. And you can monetize in today's world, you can monetize those carbon credits. And we do that in Anglo Power Gen Ghazarpur Limited, where we are using flare gas to produce power. And we trade those units in the US market. Now, what are the challenges? There are effectively two challenges in the production of hydrogen. A lot of that has been talked by Stephen and Dr. Nadeem, but I'll very simply summarize it. That's the high cost of hydrogen production, number one, very rightly said by the speakers. And the second is the safe and economical transportation of hydrogen. Now, if we break that cost, where the cost is coming from and how we can work towards it, today the levelized cost of hydrogen from natural gas ranges from 0.7 per kg to $2.3 per kg. It is based on a price of gas of about 1.1 up to $10 per LMPD. While the cost of producing hydrogen from coal varies from 1.4 to 2.2 per kg, dollars I'm talking, based on a coal price of $30 to $120 per kg. So keep that in mind. If the green hydrogen has to compete with these sources and to make commercial sense, today it's difficult. The cost of producing green hydrogen in other terms depends on three factors. And I'll tell you some solutions around that. Number one is the cost of electricity. 1 kilogram of hydrogen today requires approximately 53 kilowatt hours of electricity. Electricity constitutes approximately 70 to 80% of the cost of green hydrogen. Reducing the cost of input of electricity can bring down the cost of green hydrogen. So here one solution is, which I'm sure you all are aware, especially in the policy circle, is CTBCM. CTBCM is stuck. Why is it stuck? Because we cannot figure out or decide on the wheeling charges. In India, Thailand, Vietnam, most of Southeast Asia, where the market has been partially liberalized, electricity market, the wheeling cost for new green energy projects are zero. In Pakistan, the demand is 28 rupees today by the disclosure. It's impossible. So without giving subsidy, some sensible policy decisions can bring the cost down. And we have done the work. If you see on the slide, this is the internal work done by my team in 23, a very detailed work. And you can bring down the cost to approximately 3 kilograms of hydrogen. Number two is the electrolyzer cost. Electrolyzers are the main equipment. The cheaper electrolyzers, the cheaper the hydrogen it can produce. It's simple maths. Chinese alkaline electrolyzers, and I think Stephen touched on it, are far cheaper compared to the Western alkaline and PEM electrolyzer system. With the rapid advancement of technology, just like batteries, just like solar, just like wind, it is expected to come down significantly. So we don't have to be the first movers, but we have to keep watching the space and be ready to quickly monetize if the costs are going down. We can't stay back and just say, okay, I'll wait. Number three, the third factor in the cost and the last factor is the capacity factor utilization of the electrolyzer. What does it mean? It's the percentage measure of electrolyzers being used. Because the significance of major source is renewable energy, that is wind and solar, and sometimes hydro, as you saw, this is intermittent by nature. So that means there are times when electricity is not produced for electrolyzers. In that case, combination of battery or combination of all three sources carefully can help improve the utilization to close to 100%. Now, we know these things. We know how does it work. In Pakistan, we did a pre-feasibility of a potential place in Jimpi in Sindh. Now, I would urge that this is a great area. Kijhar Lake is right there. So you have the source of water. You have the wind corridor, one of the best in the world. It's 100 kilometers from the port in Karachi, not very far. We think it can be done. And if you combine, what really surprised me when I came to Pakistan after 20 years and looked at the projects, that we put the wind power plants, but the land between the winds is empty. So our actually per kilowatt per acre of utilization is extremely poor. So we looked at the project and we said, why don't we do a hybrid? Put wind, but then fill it up with solar, and then fill it up with batteries, and then see how the numbers work. And given the battery cost going down, it is getting close to 3 kg. The second issue I told you, first was cost, second was storage. Now storing 1 kilogram of hydrogen in normal conditions requires 8 times more space than storing 1 kg of natural gas. This is a fact and this is a challenge. Therefore, hydrogen is condensed through pressurizing, liquefaction, and chemical compounding to make it viable. Liquefaction of hydrogen lowers the transportation volume significantly. However, the process is very energy inefficient and hence expensive. Chemical compounding, such as storing hydrogen in the form of ammonia, as very rightly said by Stephen, hydrogen is nothing. It's the final product is ammonia, is very promising for storage and safe transportation. And we are in discussions with several companies, Aquapa, which is doing this in Uzbekistan with very, very limited subsidy from the government. And they are providing ammonia to a vintage fertilizer plant of the 1950s, which is currently closed. And they are doing it phase 1, and they are now moving to phase 2. Now, Uzbekistan, again, is a landlocked country. To even transport the urea out and selling would cost. Pakistan has advantage. They were actually telling us that, guys, you are sitting on a natural advantage point. GreenPro in India, it currently exports ammonia to Europe. Europe gets the companies in Europe gets tax credits from the European government. They in turn pass it on to the manufacturing of green ammonia companies. Now, GreenCo does not get any subsidy from the government. What they get is zero wheeling charges from the discos, whether they are state discos or the other central government discos, not in our case. Transportation of hydrogen from generation side to the demand side is currently costly. Trucks and ships are expensive due to the lower volumetric density. However, pipelines offer the cheapest mode of transportation for hydrogen because hydrogen travels faster than natural gas, compensating for its low volumetric density. So there are advantages to hydrogen. Now, behold, Pakistan is blessed, one of the few countries in the world which is blessed with a network of pipelines running across. Because from 1950s, we have been doing that. Hydrogen, we have looked at the data, we have worked some technical cases. Hydrogen can also be blended into existing gas networks up to 5 to 20% without any major infrastructural upgrade. A number of demonstration projects have been done around the world to examine the potential. We having one of the largest gas pipeline network in the world is a no-brainer. If near Jambir, SSGC or SNGPL pipeline is going, which has ullage, why don't we do that? Then the final point, my point is that Pakistan should also explore the opportunity of exporting green hydrogen. I already talked about it. So concluding, there are 6 or 7 questions that are still challenging today. And I would leave you with those questions and to the esteemed experts on this call to ponder on it, and maybe we continue this dialogue. So if you go to the last slide. Last slide, please. Yeah. So if you look at this, so green hydrogen converts into value-added products, which are these: ammonia nitrate, methanol, urea, or e-fuels. Now, the key challenges we have is what is the current cost of production of value-added products. Now, we partnered with Mitsui, the largest ammonia trading company in the world, Japanese. They bring the cheapest debt in the world. So debt is available if the companies they are working with are credible. Because for hydrogen, it's the execution of the projects is also important. So demand is there. It's that can we get the right partners in? So we may not get G2G subsidies, but companies are ready to partner. And these questions also we pose to Mitsui as well. What are the economics of green hydrogen derived products, and at what premium is required to achieve cost parity? This is the question we are still struggling to answer. Number 3, what are the current ways in which hydrogen is handled and transported for the industrial use? Number 4, what would be the most profitable molecules to produce in Pakistan? How can we leverage our renewable resource, proximity to port, and infrastructure for green molecule journey? Number 5, what are the options and main business models for government to enter into low carbon hydrogen space? JVs, partnerships, equity, offtake agreements, etc. And finally, what are the main projects risks which could be potential, and what would be the potential mitigation option? So we as the private sector are actively working on it. At the end of the day, my request would be technical challenges we will continue to de-risk. But if a space is created within the government where without giving subsidy, policy work is done in such a way that the inefficient subsidies are reduced, that creates automatically the space for private sector to come in and take the risk. The whole game is risk reward. And I have no doubt, inshallah ta'ala, with the quality of resource we have in this country, and this work is all done by Pakistani engineers, with a little bit of help from our colleagues in Mitsui and Aquapower. But I have full confidence with the quality of resource we have, the quality of people we have, the execution experience the private sector has, help with the government from a policy space, not subsidy space. If not immediately, if we start today, watching it in 5 to 10 years' time, we'll be able to do a commercial project. Thank you very much for that.
Oh, well, thank you so much, sir. Dear participants, the Pakistan Green Hydrogen Energy Feasibility Study report is available in a QR code that is available in your folder screen. You can download it through this code. Well, given the time constraints, I would like to invite Mr. Masroor Ahmed, Chairman OBRA, for the closing remarks. Please, sir.
Assalamu alaikum. Am I audible? It's definitely a great privilege to be part of this journey, which is the launch of a pre-feasibility study for green hydrogen. It's definitely a landmark occasion. I can fully understand after listening to various participants and consultants, there are arguments supporting this initiative, and there are arguments giving challenges to this initiative. And the biggest challenge, as the Dr. Saab says, is the subsidy, and we are under the annual program. Anything which pertains to subsidy is not kosher, at least nowadays. Now, having said that, the world has changed. The energy needs are being changed on a daily basis. And we are at a stage where hydrogen energy, the green hydrogen molecules, are now entering, or rather knocking our door. Now, why is it that? Toyota has launched a green hydrogen automobile. Hyundai has launched one of the sedan models. In our neighbor, in India, they have allowed addition of 5% green hydrogen in the CNG sectors. So it's happening. We simply cannot ignore it. That's a hard fact. It's a reality. How we do it, that is secondary. Now, when we look around, we got plenty and plenty of hydrogen in a complex form around us. Water, H2O, ammonia. We got natural gas, methane, CH4, LPG is basically propane and butane. So we got plenty of hydrogen in complex forms which required to be decomposed into a hydrogen as an element and then used as an energy. Interestingly, hydrogen itself as a strand alone does not carry any energy, which is very strange for a common person at least. So what happens when these complex compounds are decomposed by any chemical process or by superheating, and hydrogen is extracted, that amount of energy is stored in the hydrogen molecule. And when it is used as a fuel, then of course, it generates energy. So I will not go into the academic definition of what is green hydrogen, what is blue hydrogen, which is gray hydrogen. And when it is extracted from coal, it becomes black hydrogen, because that's a long lecture required, a lot of time, and I can understand it's very dark in Islamabad. Half of the participant has already left. So I will stick to the two areas where OGRA has interest. And I will not touch base fertilizer because Yusuf has already touched base on the fertilizer bit. So in the automotive sector, we have interest in OGRA because it is very, very challenging that every month we handle 9 cargo ships of crude oil, which almost cost 400 to 450 million US dollars, depending on the price. We handle 9 cargo ships of motor gasoline, which is 10% more than the value of crude in absolute terms for the molecules. And then we handle 3 ships of diesel every month. So in totality, this amounts to more than $1 billion US bill every month. This does not include LNG. This does not include LPG. So if you put everything together, in the last 12 months, it was 15 billion US dollar, which was paid to procure imported molecules. Now, in order to arrange 15 billion US dollars, for every dollar you need 280 rupees. So just think about the amount of money which is required to open LCs. And every fortnight, when we announce prices in OGRA for the finished product, we have to consider these factors like actualization of LCs, swap of LCs. So we need solutions to replace expensive molecules. We have no other choice. We have no other choice. The second area where green hydrogen has significance, and we in OGRA would be very, very keen to work together with the industries, with the potential investors, with the research institutes, with universities, is the natural gas. So I understand in US, they're already working on introducing certain percentage of green hydrogen in the main transmission lines, but that's US. Over here, as I said, we have plenty of hydrocarbons with plenty of hydrogen. The only challenge is to find an economical solution to decompose and to get hydrogen in an absolute form so that it can be introduced into the transmission lines of the two companies. So at this forum, what I would like to encourage to all the potential investors, participants, consultants, that whoever will come forward to work on that initiative, OGRA would be very happy to provide support. And when I say support from OGRA, for introduction of green hydrogen in the transmission lines, you need rules, you need regulations, you need specifications, you need standards, and of course, on top of everything, what you need is the revenue requirement of the three companies. So we'll be very happy to support the industry. We'll be very happy to support the initiative. With that, I would like to conclude. It's already very late in this summer. Thank you. Thank you very much.